Hello everyone, welcome to our channel. Today I am going to discuss basics of operation amplifiers. The topics I would like to discuss today are: first one, operation amplifier equivalent circuit; second one, op amp characteristics, both ideal and practical characteristics; and third topic is ideal voltage characteristic curve. And fourth topic is modes of operation. Are open loop configurations of operation amplifier. These are the topics I would like to discuss today. First one, the operation amplifier equivalent circuit. In the earlier videos, we have learned the internal block diagram of the operation amplifier, which consists of 4 blocks. First block, dual input balanced output. Second block, dual input unbalanced output. Third block, level translator. Fourth block, driver stage, or simply power amplifier. The internal circuit operational amplifier is very complex, which consists of more than 50 transistors interconnected with each other. So, the equivalent internal circuit, or simply AC equivalent circuit of operational amplifier, can be represented with a simple 3 components: Ri, R0, and a Thevenin's voltage source. Because there are 2 input terminals, between the 2 input terminals there is one resistance, which is the overall input impedance, and between output terminals we are using into the output terminals of the operation amplifier. The equivalent circuit of the operation amplifier can be represented with its Thevenin's equivalent model. Thevenin's equivalent model of the operation amplifier is represented with a single voltage source in series with single resistance. Here the single resistance is represented with R0 and the voltage source is represented with AOL gain component into differential input VID, where VID is the voltage between input terminals. This is our output V0, this is our input V1, this is our input V2. Let us call this as inverting input, this is as non-inverting input. So, the equivalent circuit of operation amplifier is represented with one resistance Ri in between 2 input terminals, which is called as input impedance of the operation amplifier, and with Thevenin's equivalent model between output terminal and ground. Here the Thevenin's voltage source is represented with AOL into VID, where VID is the differential input between the 2 input terminals, and AOL is the open loop voltage gain of the operation amplifier. Later we see the open loop voltage gain of the operation amplifier is much larger than 50,000. Its minimum value is 50,000 and it is more than 2 lakhs at present. That value will be little different for different manufacturers, but the open loop voltage gain is very large, and R0 is the output impedance seen between output terminals of the operation amplifier with respect to ground. So here Ri is called as input resistance. Input resistance. So the input resistance we can represent as of the order of few mega ohms. Because the input impedance is very high, the current entering into inverting input, non-inverting input will be very small. Those currents will be of the order of a few nanoamperes. And R0 is called as output resistance. Generally its value will be very small, few ohms or few tens of ohms. Because the output impedance is very less, the circuit is able to deliver maximum current to the other circuits. So it indicates the output of this operation amplifier can drive more number of circuits, and because the input impedance is very high, it will not load any previous circuits. These are the main advantages of this operational amplifier. And AOL is called as open loop voltage gain. Open loop voltage gain. Its value will be very large. VID. VID is the input differential voltage. Input differential or difference voltage, which is the difference of two input signals. Generally, we write this as V2 minus V1. Here, few points are to be observed carefully. Why the input impedance of the operation amplifier is very high? Because as we learned earlier, internal block diagram of the operation amplifier consists of 4 blocks. In that, first one is dual input balanced output block. That circuit consists of differential amplifier stages within that, which are emitter coupled differential amplifiers. Normally, the input impedance of emitter coupled differential amplifier will be very high. That's why the overall input impedance of the operational amplifier Ri will be very large. And the last stage of that block diagram is a power amplifier stage or driver stage. Normally, the output impedance of the power amplifier stage is very small. That's why the output impedance of operation amplifier is very small. By the design of this operation amplifier, it consists of so many cascaded differential amplifier stages within that. Due to this, the overall voltage gain of the circuit will be very large. That's why the typical value of this operational amplifier open loop voltage gain will be more than 50,000. Normally it is more than 10 power 5. This value will change from manufacturer to manufacturer, and the differential input voltage is simply the difference of the two input signals. Because the open loop voltage gain of the amplifier is very large, this amplifier is able to amplify very small input signals. For example, if the open loop voltage gain is 10 power 5, then if the input differential voltage VID, for example, is 1 millivolt, then V0 can be obtained as the product of open loop gain into VID. For a given value of R0, the open loop output voltage can be written like this. So this will be equal to 10 power 5 into 1 millivolt, 1 into 10 power minus 3, which will be about 10 power 2 volts, that is 100 volts. Even though this value is not practicable, this example I have given is just to understand, even though input is very small, we can get very large output due to very large open loop gain of the amplifier. Any operation amplifier for its operation requires two DC power supplies. Generally, they are represented with plus VCC and minus VEE. Both values will be equal in magnitude. For example, if plus VCC is 15 volts, then minus VEE will be taken as minus 15 volts. Both will be equal. Everybody is following these notations, plus VCC minus VEE. What we can know from these values? Operation amplifier cannot generate any voltage internally. Because of energy conservation theorem, energy cannot be created, cannot be destroyed. It can be converted. Because of that formula, the output voltage can be always less than plus 15 volts and more than minus 15 volts. In between any value, but it cannot exceed 15 volts. But if we see the above example, when input voltage is 1 millivolt, the output voltage is 100 volts. Can we get practically this 100 volts? We never get it. So what would be the expected output? It will be truncated to this 15 volts. So because of this, there will be a distortion after amplification by this operational amplifier. So all parts of the signal above 15 volts will be truncated. To overcome this problem, we use negative feedback in all operation amplifier circuits just to reduce the gain. This is another advantage of operation amplifier circuits. Our next topic is characteristics of operation amplifier. For operation amplifiers, all others have presented practical characteristics as well as ideal characteristics. So these characteristics I would like to present in the form of a table such that we can easily remember and recall. So parameter characteristics of op-amp. Parameter, ideal characteristics or ideal value, and then practical value. If you remember in this fashion, you can easily recall the typical values of operation amplifiers. So in this, the first one is voltage gain. Because for any amplifier, the gain is important. For operation amplifier, voltage gain. Generally, it is represented with the A. Open loop voltage gain or AOL. You can also represent like this. Nothing wrong in it. And its ideal value is infinite. Generally, this ideal value is represented with minus infinite. The reason is this operation amplifier is normally operated in inverting mode, so the gain will be negative. So in simple sense, we can also say the ideal value voltage gain is infinite. But practically, can we get infinite value? No. So the practical voltage gain will be very high. As we have seen earlier, the open loop voltage gain is 10 to the power of 5. Like that, it will be very high. And second parameter is input resistance. As we discussed earlier, the input resistance will be very high. So ideally, the value will be infinite ohms. But practically, its value will be very large, few mega ohms. And the third parameter is output resistance. Output resistance is 0 volts, 0 ohms for ideal case and very small practically. Practically its value will be very small. It will be about a few tens of ohms. And input impedance will be of the order of mega ohms. And the fourth characteristic, which is very important, is perfect balance. Perfect balance means V0 is equal to 0 if V1 is equal to V2. As we have seen above, the output voltage V0 is given by AOL into VID. So if VID is given by V2 minus V1. Suppose if V2 is equal to V1, then VID will become 0. Then what should be V0 value? It should be 0. Then we say the operation amplifier is perfectly balanced. For an ideal amplifier, it is always perfectly balanced. Suppose if you come to this practical operation amplifier, V0 will not be equal to 0, even if V1 is equal to V2. This is mainly due to the unavoidable offset voltages at the output of the operational amplifier. In practical circuits, what we do is we always try to minimize the effects of offset voltages and offset currents. Then we nearly get the perfect balance, but we never get a perfect balance in practical applications, which will be very difficult. The next parameter is bandwidth. Bandwidth of the operational amplifier. For ideal case, the bandwidth will be equal to infinite Hz. Practically, bandwidth will be very large. Bandwidth is infinite means, in ideal case, the circuit is able to amplify all frequency signals from 0 to infinite Hz. But any practical circuit has some limitations. It cannot amplify up to infinite frequencies. So practically the bandwidth is always limited. But here expected value will be large. But bandwidth is always limited for any given practical circuit. The next parameter is CMRR, which is another very important parameter of the operational amplifier. CMRR stands for common mode rejection ratio, and it is defined as the ratio of differential gain to the common mode gain. This tells how much of the differential input is amplified. So it is very important parameter of the operation amplifier, and ideal value of this parameter will be infinite. Practically its value will be very large. Generally it is expressed in terms of dBs. So practically its value will be about 70 dB, 80 dB, 100 dB, like that. And next important parameter is slew rate. SLEWRATE. Slew rate. This slew rate is defined as the rate of change of output voltage with respect to time under maximum signal conditions. Ideally, its value is infinite, but practically its value is very large. Some other very useful characteristics which are to be considered with the practical operation amplifiers, let us see now. Input offset voltage. These characteristics we cannot neglect when we are working with practical operation amplifiers. That's why we should know about this. So its ideal value should be 0 and practical value should be very small. Generally its value will be few millivolts, and the value will be mentioned by the manufacturer. And another characteristic is input offset current. Ideally its value should be 0. Practically its value should be very small. Generally this is expressed in terms of nanoamperes. Its value will be few tens or few hundreds of nanoamperes. And the next parameter is input bias current, represented with the symbol IB. Ideally its value should be 0 and practically its value should be as small as possible. This is also expressed in terms of nanoamperes. This value will be about a few hundreds of nanoamperes or of the order of microamperes. Another one is SVRR, called as supply voltage rejection ratio. Supply voltage rejection ratio. It is defined as the ratio of change in input offset voltage corresponding to the change in supply voltage. Corresponding to the change in supply voltage. So change in VIO, input offset voltage, divided by change in VCC plus VCC. While measuring this, the other supply voltage VEE should be maintained constant, and its ideal value should be 0 and practical value should be as small as possible. Suppose if you measure this value by keeping VCC constant, then the formula can be written as dou VIO by dou VEE when VCC is kept constant. Both values should be measured when you are working with operational amplifiers practically, and the average value is generally expressed as SVRR. For this case also, its value should be 0 ideally, and practically it should be very small. And the last parameter in which we are interested is output voltage swing. Output voltage swing means the maximum peak to peak value of the output that can be obtained by using operational amplifier. Ideally, its value should be infinite. Practically, its value should be as large as possible. For a given practical operation amplifier, its value will be always limited to plus or minus Vsat, where Vsat is the saturation voltage, or positive saturation plus Vsat, negative saturation minus Vsat. So always this is the maximum output voltage, because the DC power supply values what we are using are plus VCC and minus VEE. We never get these values. So our saturation value Vsat is always less than either VCC or VEE, magnitudes of VEE. Because of the internal drops, Vsat is a little smaller than VCC and VEE. So this is the output voltage swing that we can get by using any operation amplifier. So these values, Vsat values, will be given by the manufacturer. For example, if VCC used is plus 15 volts, then plus Vsat value would be either plus 14 volts or plus 13 volts. This value will be given by the manufacturer. In the same way, for negative saturation, if VEE is minus 15 volts, then minus Vsat value will be equal to minus 14 volts or minus 13 volts. The next topic of today's video is ideal voltage transfer curve. So it is the relation between the differential input voltage VID and the output of the operation amplifier. Here we are assuming that the output offset voltage V0 is equal to 0. Otherwise, there will be a small offset in the characteristic curve. So if we assume that the output offset voltage is 0, then the transfer curve will move through the origin on both sides. It is a straight line. After some input value, the output will be constant. This is 0. In this direction, the differential voltage is positive. In this direction, the differential voltage is negative. Differential input is negative. And this is the maximum output that can be possible, which is called as plus Vsat, and this is the maximum value that is possible on negative side, called as minus Vsat. Just we have seen above. So from this we can understand between the values of this minus VID and this plus VID, for this range of input values, the output is linearly changing. Indicates that we get faithful amplification by using this operation amplifier. Suppose if your input exceeds this plus VID or goes below minus VID, then output will be constant, that is plus Vsat. Even though the input is varying with the time, the output will be constant. Those variations of the input cannot reflect in the output. That situation we call as saturation. In saturation, we never get amplification. So, the operation amplifier should be operated within this range of input values. So, we can call this as input linear range, for which the amplifier will provide faithful amplification. And the maximum output that we can get is plus Vsat, and the minimum value that we can get is minus Vsat. This range is called as output voltage swing. We never get more than plus Vsat and less than minus Vsat. So the maximum output that we can get for any given input is between this plus Vsat and minus Vsat. This is called as the output voltage swing. Maximum output voltage swing. For better understanding, I will explain these outputs for given inputs with simple waveforms. So let us extend these axes to apply some input. Let here these are the limits, maximum and minimum. So the waveform is not seems to be symmetrical because I am unable to draw this properly by using this electronic slate. But assume that these are symmetrical, and I will change the color of these waveforms just for more clarity. So let us apply one input signal here, sine wave, like this. This is the minimum value, and let us take a sine wave like this, which is well within the input linear range, and the corresponding output what we get is extend this by using a dotted line, post this onto the transfer characteristics of the operation amplifier, and the corresponding output you can draw by drawing like this, and this will be the corresponding output. The output will be sine wave. If input is sine wave, output is also sine wave. And these are the saturation levels. Because our output is well below the saturation level, there will not be any distortion. Suppose if we apply a waveform input signal like this for the maximum range of the input, then the corresponding output will be the maximum output possible. Maximum output possible without any distortion. Please remember, these positive and negative half cycles are symmetrical. Suppose if our input is much larger than the linear range of the input signal, then what will happen? Suppose if everything goes well, the expected output what we should get will be like this. But above this value, we never get. Below this value, we never get. So, what the output we get actually is up to this portion, then it is truncated because of the saturation, and we get this portion of the input signal amplified, and again here it is truncated, then this portion of the input only we get. So, if you compare the input and outputs, these peaks are not amplified. So, there will exist some distortion. So, while we are using operational amplifier, we have to keep in mind that the operational amplifier does not enter into its saturation range or saturation at any moment of the input signal or for any portion of the input signal. The operational amplifier output does not enter or should not enter into the saturation region. Our next topic in today's video is the modes of operation using operational amplifier. Operational amplifier can be operated in three modes. One is differential mode, or differential configuration. Another one is inverting mode as a different inverting amplifier. These are also called as a differential amplifier or inverting amplifier. And the third one is non-inverting amplifier or non-inverting mode or non-inverting configuration. Whatever the word you use, simply it is called as non-inverting amplifier. So in differential mode, the circuit will be like this. We have two input terminals for the operation amplifier. Inverting input, non-inverting input. We apply two signals. One input signal at inverting input represented with V in 1 in series with its internal resistance R1, and another signal at non-inverting input represented with V in 2 in series with its internal resistance R2. These are the two signals. They may be AC signals or DC signals, no problem. And the voltage at inverting terminal is normally represented with V1, and the voltage at non-inverting terminal is represented with V2. So the differential voltage between input terminals VID now will become equal to V2 minus V1, and the final output is normally represented with V0. We know V0 is equal to AOL, open loop voltage gain, into VID. So here this can be written as simply A, open loop voltage gain we can write with A, into V2 minus V1. What is V2 here? The voltage at non-inverting input. What is its value? Suppose if you see Vi2, V into R2, V2. These are in line. How much current will flow through R2? Because the input impedance of the operational amplifier is very, very high, the current entering into the input terminals of the operational amplifier is almost equal to 0. Because the current flowing through this input terminal is 0, the current flowing through R2 resistance is also 0. I is equal to 0. Then how much voltage will drop across this resistance? According to Ohm's law, I into R2. I is 0. So no voltage will drop across this R2. Therefore, V2 will be equal to V in 1. So we can write V2 is equal to V in 2. In the same way, the current entering into this inverting input is also 0. So the drop across R1 is also 0. So from this what we can write is V1 is equal to V in 1. So in this expression of output voltage, we can write as V0 is equal to A into V into minus V in 1. So the output voltage is directly proportional to the difference of the two input signals P in 1 and V in 2. That's why this configuration or this mode of operation is called as differential mode of operation. So we can operate our operation amplifier in differential mode. Differential mode. What will be the polarity of the output voltage V0? That depends on the magnitudes of V in 1 and V in 2. Suppose if V in 1 is greater than V in 2 is greater than V in 1, then V0 will be positive. Suppose if V in 1 is greater than V in 2, then the output will be negative. So the polarity of V0 is depending on the polarity of the differential input VID. Next, second mode of operation is inverting mode. In inverting mode, we apply only one signal at inverting input. The other input terminal is connected to ground. So only one signal is applied here. That is V in 1, and the internal resistance of that can be represented with R1, and the voltage at inverting terminal can be represented with V1, and the same at the other terminal is V2. Again the differential input is VID. Then the output voltage V0 can be written as A into V into minus V in 1. This expression directly we can write because already we discussed this in the previous circuit. But here, what is the value of V in 2? It is 0. So V0 will be equal to minus A into V in 1. So V0 is always equal to the negation of product of gain and input signal applied at inverting terminal, because output is always inversion of V in 1. This mode of operation or this configuration is called as inverting mode of operation. Inverting mode of operation, or simply inverting configuration, or simply inverting amplifier. Inverting amplifier. Suppose if we draw the output waveforms and input waveforms for this configuration, how it looks like. If a sine wave is given as input signal, this is Vi or V in 1, then the corresponding output will be the negated version of this input signal. It will be like this. This is V0. Okay. If input is positive, output is negative. If input is negative, output is positive. This is the meaning of negation or inversion. Suppose if we apply instead of AC signal a DC, some constant voltage of example 2 volts, then the corresponding output will be negative value, and let the gain is equal to 1 for simplicity. Then output will be minus 2 volts. Suppose if gain is 2, then output will be 4 volts. 2 into 2, 4. Because it is inverted, the output will be minus 4 volts. Like this, we can understand the operation of inverting amplifier. And the third mode of operation is non-inverting mode of operation, or simply non-inverting amplifier or non-inverting configuration. Whatever the name we use, it is non-inverting mode of operation. So the circuit of this will be like this. Here the input signal is applied at non-inverting terminal, so Vin2 in series with its internal resistance R2, and the potential at this terminal is V2, and the inverting terminal is connected to ground. So here V1 is set equal to 0. The output voltage will be equal to A into V into, because V in 1 is equal to 0, here V in 1 is set equal to 0, V1 is equal to 0. So V0 will be equal to A V into. Suppose if V into is positive, V0 is also positive. If V into is negative, V0 is also negative. So the polarity of the output is always same as the polarity of the input signal. That's why this is called as non-inverting mode of operation. If we see in the previous one, inverting mode, V0 is equal to minus A into V in 1. So if V in 1 is positive, V0 is negative. If V in 1 is negative, V0 is positive. So always output is opposite that of V in 1 polarity. But in the case of non-inverting amplifier, non-inverting mode, the polarity of the output voltage is always the same as that of the input voltage applied at a non-inverting terminal. And the waveforms, if we draw for a sinusoidal input like this, V into, the output will be same as the input like this, V0. Suppose if we apply here a DC voltage of, for example, plus 3 volts, that the gain is equal to 1, then the corresponding output will also be equal to plus 3 volts. So the polarity of the output signal is always same as that of the input. That's why this is called as non-inverting amplifier. What is the phase difference between input and output waveforms if we are operate this operation amplifier in non-inverting mode? It is 0. Suppose if to take the case of inverting amplifier, what is the phase difference between input and output signals? It is 180 degrees. Suppose if we operate operation amplifier in its inverting mode, then you can obtain 180 degrees out of phase. So you can get a phase shift of 180 degrees. Remember this point. With this, we completed our today's topics planned for this video. If you have any doubts or need clarification, ask me in comment section. Thank you.